Welcome to the Vectors and Scalars simulation. Are you ready to get other people's hands dirty in a place far away from Earth? This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Open the locker to your left. Put on a lab coat. Enter the laboratory. During this virtual simulation, you will be introduced to the fundamental physical quantities of displacement, distance, speed, and velocity. You will understand the difference between a vector and scalar quantity and identify the magnitude and direction of a vector. By the end, you will be able to define the components of a vector and solve basic engineering problems. Are you ready to guide a mission of astronauts on the surface of Mars? Only a few are lucky enough to get access to this room. I wish there was time to chat with you, but an important announcement is coming in. We should stop what we're doing and pay close attention to the message coming from the outer space. Let's proceed quickly to the control panel. Workbench 1 has a screen that provides you with a direct connection to everything happening on the surface of Mars through video recorded from the nearest satellite. Go to Workbench 1. Switch on the left monitor to see what is happening on the surface of Mars.
The Labster exploration rover has become stuck in some soft soil on the surface of Mars. LRD-M was sent to perform a geological analysis of Martian rocks and planetary surface features, and now the entire mission is in jeopardy.
We need to move fast then. What are our options?
2 astronauts have recently landed on the surface of Mars. It's your task to guide the 2 astronauts from the nearby spacecraft to release the rover. Satellite images will help you guide the astronauts towards LRD-M.
Let's start working at the control panel. We have to locate everyone on the surface of Mars and make sure we give the astronauts the correct directions to guide them towards the rover. Before guiding the astronauts towards a specific point on the surface of Mars, we should define their current location on the map. It is also important to determine the exact location of LRD-M. Activate the coordinate plane. The display on the right shows a coordinate plane. A coordinate plane is a system which uses one or more numbers, or coordinates, to uniquely determine the position of a point or other geometric elements. In our case, these points are the astronauts and the rover. For this mission, we will be referring to a unique coordinate plane called the Cartesian coordinate system. Locate the spacecraft on the Cartesian coordinate system. Check out the satellite image on the left monitor, and then try to assign the position of the astronauts and rover to the numbers in the coordinate plane. Each dot could be an item with a unique position on the surface of Mars. The green dot on the astronauts and the rover, as seen from the satellite image, defines the position of each item on the coordinate plane. The position of the spaceship in both images will guide you to click on the correct dots. Determine the coordinates of the astronauts and rover. Good job locating the astronauts and the rover. The next step would be to guide the astronauts back to their spaceship as soon as possible. They have to go there and pick up the right tools before heading towards the rover. I have prepared a list of questions which, if you answer correctly, will give the astronauts all the information they need to navigate. The matter is very urgent, but we have to act carefully. First, let's start with astronaut A. How is astronaut A going to move in order to cover the distance from -300 to 0 to get back at the spaceship? That's right. Astronauts wear special uniforms that allow them to move outside of the spacecraft. Anytime an astronaut gets out of a vehicle while in space, it is called a spacewalk. During spacewalks, the astronauts are breathing and drinking inside their suits. What or who is located at 100.-200? You are the master of the Cartesian coordinate system. You have done an amazing job so far. The next step would be to guide the astronauts towards the spacecraft. Guiding someone towards a certain position requires the determination of the direction of the movement. Let's go to the next workbench to find out more about the direction of vectors. Go to workbench 2. During spacewalks, the astronauts need clear instructions in order to locate their target. Asking them to move 10 meters doesn't mean much since they wouldn't know in which direction to move. In order to be precise, you should define both the magnitude and the direction of their movement. For example, move 10 meters north. Your next task is to position the arrows correctly in order to go from one point to another. All the arrows on these pieces of paper have the same length but different orientation. Or as a physicist would say, all the vectors have the same magnitude but different direction. Even though the problem we're facing with the astronauts requires a two-vector addition, in many cases, you may need to add several vectors to understand the overall magnitude and direction of a movement. If your workbench is facing north according to the compass bearing to your left, and assuming that you need to go from the dot on paper A to the dot on paper B, which would be the overall direction of the route you would follow on the workbench? Superb. The piece of paper with point B is located at the bottom left side of the workbench in comparison to point A, which is at the top right side. Arrange the papers to go from the dot on paper A to the dot on paper B. Good job positioning the vectors in the right order to go from point A to B. Summing up all these small arrows will result in the overall direction of the movement. The sum of all these vectors will start from the tail of the first arrow and go all the way to the head of the last arrow. Using the head-to-tail method to add more than two vectors is a very easy and graphic way to sum up many vectors at once. Go back to the previous workbench and apply all the things you have learned so far. Go back to workbench 1. Both astronauts have to go back to the spacecraft to pick up a hammer and a shovel. That's the only way they could release the rover from the soft soil. The following questions will give hints to the astronauts about how to cover this distance successfully. Which is the route of minimum displacement for astronaut B from his current location, back to the spacecraft to pick up the hammer? Exactly. The green arrows define the magnitude and the direction of the traveled distance. The total distance traveled is the sum of the magnitude of these arrows without taking into consideration their direction. In other words, in all three cases, the diagonal arrow signifies the total displacement. Which is the route of minimum distance that astronaut B needs to travel to arrive to the spacecraft? That's right. The minimum distance refers to the least amount of ground the astronaut will cover to reach the spacecraft. And since it is a scalar quantity, the direction of the movement doesn't affect the answer. Which is the distance traveled and which is the total displacement of astronaut B, in the following case? No, this is incorrect. Please try again. Great answer. The distance refers to the amount of ground he covered to go from one place to another, whereas the displacement refers to the length of the line that connects one place to the other regardless the route he followed to go there. You answered all the questions and gave valuable information to both astronauts, meaning they can quickly get back to the spacecraft to collect their tools. Check out the left screen to actually see them on the satellite image. Be patient now, a few more questions and then the astronauts will have all the tips to reach the rover. Astronaut A can cover 10 meters per minute walking with a heavy shovel. What does this sentence describe? Exactly. Since velocity is a vector quantity, if you wanted to describe it, you needed to define both the magnitude and the direction. 10 meters per minute defines the magnitude, and therefore the scalar quantity of the speed. How much time do the astronauts need to reach LRD-M when covering the distance from the spacecraft to the rover? Remember that the distance to the rover from the spacecraft is 500 meters and the velocities are 10 meters per minute for astronaut A and 20 meters per minute for astronaut B. Exactly. According to the equations below, in 50 minutes both astronaut A and astronaut B would reach the rover. Time alpha refers to the time astronaut A needs to go back to the spaceship and time beta refers to the time astronaut B needs to cover the same distance of 500 meters all the way to the rover. V is the velocity and x the distance. Using the Pythagorean theorem, which is the distance of the spacecraft to LRD-M, the C line represents the total displacement and A and B lines are the x and y coordinates. Superb. Check out how the distance x is calculated in a right triangle using the Pythagorean theorem. The astronauts have reached LRD-M using your correct answers to the questions. Now it is time for some manual work. Both astronauts have to remove the mud around the wheels of LRD-M to release it from the soft soil. Click on the left screen to have a look at the surface of Mars. Okay, the astronauts managed to remove the soil from the wheels of the rover. It's rather obvious that in order to escape from the area of soft soil in the pit the rover has to be pulled in the direction of the safe path. Go to workbench 3. Unfortunately, the astronauts cannot push the rover, nor can they drag it as they might become trapped in the soft soil themselves. The only thing they can do, is to put some ropes around it and pull it in the direction of the safe path. The arrows on the workbench represent the force each astronaut has to apply to pull the rover free from the mud hole. Since force is a vector quantity, each arrow represents both the magnitude and the direction required. Your task is to select the correct combination of force vectors, so that the vector sum aligns with the green outline. Remember that the sum of vectors determines not just the magnitude, but also the direction of the resulting vector sum. So if you don't choose the right combination of forces, then the rover will fall into the mud hole, either from the left or from the right of the safe path. Pull the rover out of the pit. It smells like freedom from here. The two arrows you chose were the components of the force required to release the rover. Wanna try more combinations of forces? You've made a great estimation of the forces required to release the rover. 70 newtons towards the direction of astronaut A and 100 newtons towards the direction of astronaut B. Let's go back to the workbench and see if all the knowledge you gained today assisted the mission of astronauts to release the rover. Go back to workbench 1. With your help, the astronauts managed to release the rover and now they can go back to their spacecraft and continue with their original mission. Let's imagine that the astronauts were irresponsible and they decided to drop their tools there to go back faster to the spacecraft. If you drop something on the surface on Mars, will it drop with the same speed as if you had dropped it from the same height on the surface of Earth? No, this is incorrect. Please try again. What a rock star! The acceleration of gravity on Mars is almost 3 times lower than on Earth, meaning that an object falling from the same height in both planets would reach the surface of the Earth much faster. Check the satellite view on the left monitor.
Great job. Thanks for saving the mission.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.